So welcome guys, welcome to Cheenta School of Statistics and Data Science, and we'll be discussing today some ideas of consistency and other problems that our students have decided to discuss and are facing issue in. And if there's no such doubts, we will move ahead to jam question solving very soon. As Nikhil has asked, we will be starting with a few ideas of consistency. I've discussed consistency in our probability CC. I don't know. At least I have discussed consistency in our past problem solving classes. Do you remember the theory, Nikhil? Like what I have discussed? Okay, so let's say, so this is what we are discussing about. So I think you guys are not making. Did you make cheat sheets, Nikhil? I don't know if you have made it or not. Like you should be making cheat sheets in the sense that they help you to what I'm telling. I have already told. I remember you teaching you this. So did you make this, Nikhil? Like I'm just asking, or no, maybe.
Yeah, like I've made notes for everything that's there.
Okay, so now you have to tell me like what are the topic, what are the ideas. I've discussed certain ideas and results of how to approach consistency problems. Do you remember that? So I have given a decision tree, that this is a way to approach a problem of consistency, given the theory. Do you remember that? Mm-hmm.
Like,
Bolo? It's okay, you can see your notes. It's so totally fine. You can see your notes. I'm not asking you an interview question.
no, like one thing was to check like we need expectation to of the statistic
Okay,
should
so
converge to
here's
should
a
be.
okay. I understand. So here's a deal, okay? So whatever I teach today, you should make a notes of that and send it to me after the class. Okay? Done? Because I understand the reason you are like, if you face a problem in something you already taught, the reason is that you have not taken notes or not taken that idea that I have discussed. Okay, so this is very important and this is very high time that you should be taking down ideas, and this notes it should be in your cheat sheet. Okay, whatever you're going to do before the exam, and this is super important. Take a Nikhil, done.
Yeah, I will send notes.
Very good. Okay, so coming back to consistency, what is consistency, guys? So it's a property of an estimator, theta hat.
Hello.
It's a property of an estimator, theta hat. Okay, so which is a function of the sample. So x curl is the sample x1, x dot, xn. And this is the property of the estimator theta hat. This is an estimator theta, which is function of the sample. Now, the goal is the following. The goal is that the good property of this is we must show that this is close to theta in some sense. So how we show that? We show this.
Hello.
One second. One second, guys. Yeah. So coming back to the ideas we are discussing, we need to show that theta has is close to theta. So what we measure? How do we measure that? We measure that by this by in a probability stochastic framework where we say that probability this theta hat minus theta. Okay, this is greater than epsilon is going to 0 or 1. Tell me. 0 or 1? Tell me, 0 or 1? So this is a function of the sample size n. So this is going to, tell me, 0 or 1? This is something you should be.
1.
1. Okay. Who are 1 and who are 0? Okay, I need a raise of hands now. Okay, how many people are 1? Raise your hands. Srijan is 1. Another person told me 1. Okay, Vendrila 1 or 0? Okay, Prodipta 1, Vendrila 1 or 0? Okay, you want to answer? Dibangana 1 or 0? Okay, Nikhil 1 or 0? What does the intuition say, guys? Why you are learning? Why you are, trying to memorize? What does the intuition say? What is the meaning of this? What is the meaning of this? Anyone who wants to explain what is the meaning of this? Because see, you have only 1 month left, okay? And at this time, you should be very comfortable with this. I mean, this is an yes, always. You should be comfortable. There is no like, if you're not comfortable, maybe you're lagging behind something. So, what is the meaning of this Andrawala term? What is the intuition of this?
Distance between the parameter of the estimate.
Very good, Sriteja. So the distance between parameter and estimator greater than theta means? Very good. So this is the distance between parameter and estimator greater than theta means? Greater than epsilon means? So it's a certain number, right? So it means it should be very as close as possible. So greater than theta, greater than epsilon must be not happening, right? If it's a really good estimator, right? So that's the idea. If it's a really good estimator, this must not be happening. Like this should be going to 0, not 1. Okay. So always think of intuitions, don't think of formula. Statistics is built on intuitions, and then the intuitions is mathematically formalized. You're doing the wrong way. You are learning the mathematics and you're forgetting the intuitions. That's not how it works. Okay. I must be very strict at this point of time. You have only 1 month left. Okay. These are the silly mistakes that you do. Intuitions are the only thing that can help you. Okay. Remember that. Anyways, so this is the idea. So it's going to 0. If it was less than epsilon, then it would have been 1. So whatever epsilon you take, it should be always less than that. That means it's actually 0, close to 0. So that goes to 1. So remember this, okay? This is very, very important. Very, very important. Don't confuse this. Okay. Very good. So now coming back to the next part this is the definition. Okay. So an estimator is consistent like this. So now the question is that how to show the existence of how to show that an estimator is consistent, guys. How to show an estimator is consistent. One way is doing the raw way, okay? What do I mean by the raw way? I mean that you just do it like, it's a bashing way it's called. It's like you just find out the probability. It's like way one way of doing this. So you can consider this as results. It's called first principle. Okay. So what you do is that you just calculate. So you know theta hat. Let's say you know theta hat. Let's say it's an order statistic. Okay. Or let's say it's a function of order statistic. Or let's say it's x bar. Or it's like a square. So the idea is that it's something maybe whose distribution you know. So if you know the distribution, then only. So it's distribution you know. If you know the distribution, then you can calculate the probability that theta hat minus theta is less than epsilon. You can calculate this probability now, which is equal to probability of theta hat less than theta plus epsilon and greater than theta minus epsilon, theta hat. Now you can maybe find out the distribution of this theta hat ka distribution minus theta hat ka distribution, like the probability of this. And then this is a function of n, right? Now you show that it goes to 1, or you can just take greater than epsilon and it goes to 0. It's a 1 minus this only, right? So if it's only if you know the distribution of theta hat, okay, you know the distribution of theta hat. This is one way of doing this. Okay. Number 2 way, this is like it's called the first principle. You're just calculating it. But often the distribution is very hard to find. Okay, it takes time. So there is a way number 2 also. These are the things it should be in your cheat sheet. Okay, the methods of doing it. This technique should be there in your cheat sheet. Because now I am not teaching you the theory. It's no doesn't make sense to teach you the theory now. It's like if you don't know the theory, it's gone. You're gone in that case. Don't read that part. It's like now it's revision time. That's why I'm like I'm bringing out these ideas of techniques. Although I don't teach this during the full length courses, okay? Because that's now how it's taught. Like we go to the basics of that. So now the next way to is the Chebyshev inequality way or the mean variance method. So what is this mean variance method? The mean variance method is equivalent to the fact that if theta hat n is what? Theta hat n is a function of n. So if expectation of theta hat n is going to 0, theta, sorry. Yes, the bias is going to 0 and the variance is going to 0. If it's unbiased and it's going to 0, the variance is going to 0, then theta hat is consistent. It's called improbability convergence also. This is called improbability convergence. Okay. You can also do like this. So understand that this doesn't need, remember this very carefully, this doesn't require the distribution of theta hat. You just need the variance and expectation, which is easier to find. Just variance and expectation, mean and variance. So you know that, that's good. Often it's easier to find. Okay, often these are easier to find than the distribution itself. So it's up to you what you want to use. Okay, this is way 2. Okay. What other way? The way number 3 is the following. It's using the properties of improbability convergence. Okay, what are the properties of improbability convergence? Maybe, so this is something that a prerequisite is the following, that you already know, some good estimate of the consist, some good consistent estimators. Maybe you know some good consistent estimators. Maybe you know that. For example, MLE is consistent and is a consistent estimator. So you can always find an MLE if you know the distribution. So you can understand it also requires a distribution. You need to know the distribution, or maybe not. Like maybe you know the MLE. Okay, so to know the MLE, you have to know the distribution also. So MLE is a consistent estimator. You know that. You also know some other consistent estimators, maybe, like you know that. But one idea is that ML is this is a very good starting point. ML is a consistent estimator. So using this and the results of the probability in convergence, you can find new estimators which are consistent estimators. So using this and the probabilities, using this blue star and yellow star, you can find new theta hats which are new theta hats, which are consistent, which converges in probability to theta, that is consistent. So for that we need to know the properties of improbability convergence. We need to know that, right? So what are those properties of improbability convergence? So we'll just, you need not know the theorem as of now for IIT JAM, but you need to know it for ISI MStat, because ISI MStat is of course something different. So you need to know that. And let's revise the improbability convergence now. So improbability convergence, if you look into, it's very basic stuff though. So one thing is that if a sequence, so some results I should tell you, properties of improbability convergence. So this should be in your cheat sheet. And I have taught you so many times, just like you have to put it in your cheat sheet, but you have not done it. This is not done. You're just ruining your time, not yourself, but your time. That's it. I have just taught you exactly the way you need to write it in a cheat sheet, and you have not done it. This is not done. Anyways, properties of improbability convergence, like Nikhil, do you remember that I have taught this before? Hmm?
Yes. My thing is more mainly problems. That's it. I have notes for this.
Okay. So, okay, anyways, I'm repeating this so that you understand like what are the usefulness of this. So I will be showing problems like this, okay? So now, let's check this out. Um, so let me just, okay, let me just check out the probability in convergence. So one idea is this, that a sequence, if it converges to A, it implies that that sequence converges in probability to A. You can just assume that, because the probability is always one, like I mean it's equal to, like, you can easily prove this. Okay, it's easy to understand. What else? If xn converges to A in probability x, and yn converges to P in probability, then xn plus minus y converges. Okay, so you can consider xn in terms of just estimators. Also same goes for xn multiplied by this, and also xn by yn if yn is not equal to 0. Okay, so you can use that. I think it's just give me a minute. I think it's convergent. Is it just give me a minute. No, yes, so that's fine. Yes, I think it's correct. Okay, so something else is the following, is that yeah, I think these are the only properties that are needed. Okay, nothing more is needed as of now. If you can use these properties, it's done. I mean, you can only use these properties. These are the only properties that are okay. There's another property which you can use is I think that continuous mapping theorem. No, I think this is, oh, okay. I forgot that. So it's like constant also. Like if you just multiply a constant, that's also convergent, in probability. So, and this is very easy to understand. So these are the properties that you need. Okay. So these three ways are the only three ways you can use to show the consistency rather in probability convergence. Okay. Now let's do some problems out here. So let's do problem number one. The problem number one, let me check. Mm. Let me just check. Okay. This problem. Okay. So we all know that x1, x2, xn follows certain distribution, okay, with mean mu, like certain distribution with mean mu and variance sigma square. Okay. So first question I ask is that a very good estimator of this is what? Mu hat is xn bar. And a very good estimator of sigma square is what? They give me two estimates of sigma square. Can you tell me that which are the two estimates of sigma square it can be? So here it's this. So what are the two estimates of sigma square? Tell me. This is something you should be telling me. This is some really good revision. Tell me good estimators of two estimators of sigma square. Sample variance. Sample variance. So you're telling this estimate of sample variance. What is the EMV of sigma square? Do you know that? Is it the sample variance? What is the EMV of sigma square? Tell me. There are certain things you should be knowing right this moment, at this moment of time. Okay, the correction one. Okay, so you're telling that this is a good estimate. Fine. This is a good estimate. What other estimates are there? Tell me. What other estimates are there? So there was a problem in our mock test also, that if mu is unknown, then this is a good estimate. But what if mu is known? You know mu is equal to 2. Then what is a good estimate? Tell me. What is a better estimate? If mu is unknown, then you represent the value of x bar. But what if mu is known? What is a good estimate then? Tell me. This is something you should be telling me, guys. I mean, what is a good estimate if mu is known? Tell me. Tishika?
replace x bar by mu and 1 by n instead of 1 by n minus 1.
Very good. So yeah. So 1 by n, summation of 1 to n, xi minus mu whole square, because you know this is a better estimate than this. Because why it's a better estimate? Because here you're replacing mu by x bar, so you're losing information about the actual stuff. If you calculate the variance of both of this when mu is known, you will see this is coming out to be a lesser variance than this one. And it makes sense. It's a better estimate. Both of them are unbiased, but its MSE is better than this. When mu is known, not unknown. When mu is unknown, then it's a parameter. It cannot be an estimator, right? Estimator cannot contain the parameter. So that's the idea. Okay, so now coming back, we get that these are the two estimates. So now my question to you is that how can you show that xn bar is consistent or not? Can you tell me xn bar is consistent or not in both the cases? Are all of this consistent? Are all of this consistent? What do you think? Here you don't know the distribution, so which result you will use?
We can mostly use mean variance method.
Of course. So use mean variance method. Tell me the variance of this. Tell me the mean of this. The mean of this is x bar. So mean of this is mu, and the variance of this is
Sigma square by n.
So is this consistent?
Yes.
So it's going to 0 and it's going to mu. So it's consistent. Right? So what about this one? The next one, when mu is unknown. What if mu is unknown? What is the expectation of this? This is unbiased, right, guys? This is unbiased for sigma square when mu is unknown. This is UMVV. This must be unbiased. So this is sigma square. This is also sigma square when mu is unknown. These are all UMVV when mu is unknown and mu is known respectively. This is a result that should be always in your mind, guys. This is something that should be always in your mind. High time. So they are unbiased. So what is the variance? How can you understand the variance? This is a super important problem, okay? You should know how to find the variance. Okay, what if I tell you, maybe it will be hard for you to find the variance here. What if I tell you this is normal? Then can you find the variance? What if I tell you this is normal? Then can you find the variance? That's my question. Hello guys, hi. Are you here? So this is Srijan. Yeah, very good, Srijan. So you're right. So when it's normal, we know that n minus 1 sigma s square by sigma square follows chi square n minus 1. Similarly, here we know n, in this case, n times this, let's call it s1 square, so n times s1 square by sigma square follows chi square n. So from this you know the variance of this, you know from here, right? So therefore you know the variance from here. So iska variance is twice into n minus 1, right? So therefore you have to divide by n minus 1 and sigma square, it will be therefore proportional to 1 by n, and it will also be proportional to 1 by n over here. So it goes to 0. You can check that. Did you understand what I told, or I will share again? Let me share again. So n minus 1 let's call u to be n minus 1 a square by sigma square. Let's call it u1. When mu is unknown, this follows chi square n minus 1, and u2 to be n times s1 square, that is the other one case when mu is known. This follows chi square n. So therefore the variance of u1 is what? The variance of u1 is n. One second. ভাই আমি ক্লাসে আছি তোকে একটু পরে কল করছি। ওকে। Yeah, so the idea is that variance of u1 is twice of n minus 1 and variance of u2 is twice of n, right? And from here you can understand that you can find the variance of s square. So therefore variance of s square is nothing but, you can understand it's nothing but you have to multiply s sigma square, so it's sigma to the power 4 by n minus 1. Since you're dividing by n minus 1, it's n minus 1 whole square times 2. And here variance of s1 square will be twice sigma square by n. So you see that they are proportional to n and n minus 1 and n. So it's going to 0. So this is super important, guys. This you should know how to do the steps. All the steps are super important. Okay? So you should know the result of all of this. So what I'm telling it's like, therefore all of you are using here the mean variance method, right? Because you don't know the distribution. Even if you know the distribution, it will be hard for you to calculate the whole probability. So you just focus on the mean and variance. So this is the first thing that you always should apply. Or maybe the third method. The first method should be applied always at the last when the other two methods are not working. So you can easily tell it from here. These are the MLEs in the corresponding cases. So they are in probability convergent. They're consistent. So you can directly tell from there. Since the MLEs are consistent. So this is also the MLEs, right? This is also the MLEs. I think the MLEs in this case is not this, but it's 1 by n. So I think in that case, when sigma is unknown, I think MLE is this. As far as I remember, I may be wrong. So this is consistent for sigma square. So what you do is that you also know that 1 n by n minus 1, this in probability goes to 1. Since it converges to 1, this also probability converges to 1. Therefore the multiplication of this two by the result in probability convergent, it's 1 by n minus 1. Okay, does it make sense, guys? Nikhil, are you understanding? I don't know if you have done this problem before or not. Okay, sure. Okay, so let's do some more problems. So this is something these are the basic things that you always ask. So I have discussed the last two methods already here. The first method is not discussed because it's very lengthy. So last two methods are mostly used. Okay, let's see what else is there. So also you have something else. Do you know something else? I have already missed something. Something I missed is that ML is a consistent estimator. Also there is another consistent estimator. Can you tell me? It's a very good estimator. That's a consistent estimator. Can you tell me? Apart from MLE, the result, there's a good theorem which tells you that there's something consistent estimator. Another thing. Can you tell me which is that? Romit?
Sample mean is consistent for population mean.
Sample, we already showed that, no? Sample variance or concept. Okay. No, okay. I am coming to that. So let's see what Shoptoshi has to say. Method of moments, no. You're close to that, so there is a result that tells you that something is always in probability convergent to something. It's a very known result, you always use it. It's almost like central limit theorem. It's called weak law of large numbers. It tells you that xn bar converges in probability to the mu. You can also tell it from here also. Right, guys? Yeah? Does it make sense? Romit, do you remember now? So these are the two things that are very important. Now you can combine these two, okay? Now you can combine MLE and xn bar, okay, to find out something really interesting. You can always do that. You can always do that. So you can combine these two now. For example, let's say x1, x2, xn follows uniform 0, theta. So what is the mean? So xn bar. So what is the mean of this distribution? Tell me.
Theta by 2.
Theta by 2. So you get that xn bar by weak law of large numbers converges in probability to theta by 2, right? And xn, the large like the MLE of this is xn, right? This converges in probability to theta, right? So you get two estimators like this. So you can find now infinitely many estimators like this. Like, you can find out alpha. So any alpha, twice alpha xn bar plus 1 minus alpha maximum of it always converges in probability to theta. I think I'm doing a mistake. Anything with this. Yeah. So you see the applications of that now. Now you will be given options like this. Various form of alpha ke liye. Does it make sense, guys, now? How it's done? How the way number 3 is done? So this is a complete cheat sheet for consistency. You can use that. What I am discussing now. So there are two cases. You just use the first principle, or you use the mean variance stuff, or you use that certain MLE, certain improbability convergence. You use that to form new consistent estimators. Okay, that's one way out. Did you understand, guys? All of you? Very good. So can you use now to show that sample variance for mu unknown, for mu known, let's say. So we also need to know whether we showed it for normal, right? Can you show for non-normal stuff that 1 by n summation I from 1 to n xi minus x minus mu whole square, is this convergent in probability to sigma square? What do you think? Yeah, tell me.
Here mu is known, so we define a new random variable y.
Very good.
That is xi minus mu whole square.
Very good.
Then
so you know that xi or IID. So what you do is the following. You define yi to be xi minus mu, right, whole square. So therefore, if you apply now WLN on yn bar, you see it's nothing but this. Now by WLN, this converges in probability to the expectation of this. This guy is sigma square, so it converges in probability to sigma square. by WLN. Does it make sense, guys? Can you show for mu unknown? Can you show for mu unknown? Mu unknown is a bit tough because the extent bars are changing every single time. So how can you show it for that? Tell me here. How can you show it for here?
You can write any central moment in terms of row moments.
Good. Okay.
And row moments are consistent, but sample row moments are consistent for population row moments. Then apply probability theorem.
Okay. So do you understand what he told? Did you understand what he told? Anyone need to understand? He told what he told? He told that, see, we can write this function in terms of what? Let's take an example. So if you expand this function, what will you get? Any ideas? What will you get?
By square.
Right? Easy, right? So now you know that this converges in probability by WLN. Here you take Zi to be xi square. Okay. And by WLN now, you get that this one converges in probability to expectation of x1 square, right? And this converges in probability to, say, x bar converges in probability to what? Sigma square? Sorry, mu. So by probability xn bar whole square, so multiplying this to xn bar whole square will convert in probability to mu square, right? Which is equal to expectation of x1 whole square. So subtracting this will convert in probability to expectation of x1 whole square minus this, which is equal to sigma square. So done. Do you see the entire theory is built upon these three results? The most important two results are the last two results. Okay? The first one is used for special cases where you can't use the last two results. Does it make sense, Nikhil? Do you get the whole picture out here?
Yeah, I got it.
Okay, perfect. What else? Let's see. So we can only, so therefore we have understood the sample mean, the sample moment. So using this results, a lot of these results like this, we can show also that in method of moments, we use now that 1 by n. So this whole to the power n converges in probability to expectation of the the population moment. the population, the nth central, no, not the central moment, but the moment. So by WLN. So WLN is really powerful. Okay, so you can use WLN and mix MLE to get a lot of beautiful and new things. Okay. So there is no other techniques over here. Do you want to do more problems on this? Like I don't, or do you want to move on to some other new things? Tell me, Nikhil. All of you, did you understand this, or do you want some more problems on this?
No, we can do something else.
Okay, did it do a good revision for you? Is it fine? Okay, very good. So let's see. Okay, so let's do some therefore random. Okay, let's see if I have any problems. Let's see if I have any interesting problems. I will do just one problem like that. Just give me a minute. Okay, so let's do this last problem. So of consistent estimators. It's like a two sample problem of consistent estimators. Okay. So the problem is this, that x1, x2 dot xn follows normal mu x comma sigma x. y1, y2 dot yn follows normal mu y comma sigma y. Okay. So you understand that, let's say you want to understand. So in fact, this is one of my research problems. I'm going to work on this problem maybe in the future, recently in my PhD if I get one. So it's like, a good idea is that it's a multivariate case, but idea is that whether their means are equal or not, like in the multivariate setting or different setting. But the idea is that the mean are equal or not. Is their mean equal? Let's say this is H naught. I'm just giving you a motivation of the problem, why you're interested in the following problem that I'm going to understand, okay? Because motivation and intuition is really important to understand statistics once you have learned all the techniques. Till you have learned all the techniques, you need to know the theory, but once you have learned all the techniques, you need to know the motivation. Otherwise, it will become very dry. So you need to know, tell the hypothesis versus this. Okay, let's say this. It's called a two sample test. So the question is that, to understand this is equivalent to the fact that H naught star that mu x minus mu y is equal to 0 versus mu x minus mu y is not equal to 0. So if you consider this is a single parameter mu, so the question is that, as I have told you, I already questioned you last day, you know that how the hypothesis testing is done, that we need to find a very good estimate of mu hat. A very good estimate of mu hat. So how do you find a good estimate of that? How do you find a good estimate of that? That's the question. Okay? So, any ideas how do you find a good estimate? What is a good estimate? What do you think? Intuitively.
Sample mean of x minus sample mean of y.
Okay. So let's find out. So my question is that, can you find out What is the, like, my question is the following. So since you're all, so my question is the following. This is a parameter, so it makes sense to ask the following questions, right? That what is the MLE of mu x minus mu y? Another question, what is a sufficient statistic of mu x minus mu y? What is a consistent statistic? Okay. What is a complete sufficient statistic? What is the UMVV? So main idea is find the UMVV and consistency. Both are, like, others are related to each other. MLE, sufficiency, and MLE. These are the main three ideas that you can understand. So can you find out this? So what is a good estimate of that? Can you find out, like, yeah. Also, can you find out the likelihood ratio test of this? Likelihood ratio test. So these are the questions that can come. These are the questions I'm writing. I'm just making it right away. These are the questions. That's how questions are made in exams. That's how it be made in mock tests also. The question is that find the likelihood ratio test. Okay, because it's a both side test. UMP tests always don't exist. Okay, both side test UMP test always doesn't exist. The question is that, therefore, how do you find it? So therefore, when both side tests are there, we usually do likelihood ratio test. Okay, because UMP test doesn't exist. Uniformly maximum powerful test doesn't exist always. So why does likelihood, like, what is the idea of likelihood test here? What is the good likelihood test over here? It makes sense, right? It makes sense to ask. Okay, so we'll addressing these questions. I don't know, like, how much time is left. Okay, a lot of time is left, so we'll be addressing these questions now. See, I just made out this question right now, so it will be a very good revision of all the ideas together. Okay, it's a new problem and we can make sense of all of this. Okay, let's do this. So how will you find the understand? So on this, understand very carefully. Consistency doesn't require distribution assumption. So MLE requires distribution assumption. Sufficiency requires distribution assumption. Okay. Completeness may not need distribution assumption because it's expectation of that. Okay. So consistency doesn't need distribution assumption. Okay. MLE needs. Sufficiency needs. So UMVV, yeah, UMVV के लिए you need to know a complete sufficient statistic. For that you need to, like, know the distribution in some sense. So yeah. So consistency के लिए not. So there's something. Where will we start? Do you want to find the maximum? Like, tell me what you want to find first. It's your problem now. I've given you open problem now. Like, maybe you've not solved it before. So which one you want to solve first? I think we should solve first, is then go on to the likelihood ratio test of this. So how will you find the MLE over here? Tell me. How will you find the MLE over here? Tell me, guys, how will you find the MLE over here? Any ideas? The two sample problem is given over here. How will you find the MLE? Tell me, guys. Tell me, this is easily doable. So what property of MLE you need to use here? How do you find the MLE of, when let's say, how do you find the MLE of mu to the power n?
That it was invariance property.
Very good. So use the invariance property over here. We first find the MLD of this, then we find the MLD of this, and therefore the MLD of this comma this or function of this is equal to mu x minus mu y. इसका MLD होगा क्या? इसका MLD होगा right by invariance property of normal MLD maximum likely estimator. Sorry. Does it make sense, guys? Does it not? Let's go to the theory first. Which theory is important? Does it make sense, guys? Did you understand this? So therefore, you need to find the first the MLE of mu x and mu y, and you can just subtract it. That will be the MLE of this, right? All of you understood this step? Very good. So let's find out the MLE. How do you find out the MLE of this? Two samples are given. What is the first step in MLE? The first step is find the joint distribution. So you have to take the joint distribution of x and y together. X curl, y curl. Write the joint distribution. Okay. So here in the distribution, so let's take normal. Okay. So you need the distribution, joint distribution. So let's take normal. So I'm taking the normal. You get that? It's a product of. We can even take different sample size also here. The product of the some constant. There is some constant always. Let's not take the constant, like product of 1 by sigma x exponential half xi minus mu x by sigma x whole square, right? Prime product of same goes for y. Let's take a different sample size m because it can be different sample size, right? 1 by sigma y. It looks like a very hard problem, but you will see it's not a hard problem at all. It's not at all a hard problem. It's just basic mathematics. Write this, right? Now, when you do the product of this, what do you have to do? You have to take the log likelihood. When you take the log likelihood, observe that then you have to differentiate with respect to what? With respect to mu x is equal to 0, then mu y is equal to 0, right? So let's do that. We must understand something over here. Let's take, this is called meta logic, okay? So you see, if you didn't have yi, and if we have yi, okay, does it make any sense to the MLE of x bar, x mu x? That's the idea. So yi, and because yi contains only information about mu y and x sigma y, right? So yi doesn't contain information about mu x and sigma x. So when you do the derivative, this thing will go away. This thing will get cancelled already. It will be equal to 0. So therefore, the MLE of mu x is what? Is x n bar. And sigma x ka MLE is n minus 1 by n s square x. Right? S square is 1 by n minus 1. So I do it because of the issue of the unbiasedness. And similarly here, इसके लिए also mu y hat MLE is ym bar and sigma y of MLE is m minus 1 by m sy square. Did you understand, all of you guys, this one? Did you understand any doubts? Did you understand the basic logic idea? The idea is that yi is not giving extra information about xi and xi is not giving extra information about yi. So therefore, both of these are giving extra information about each other. So therefore, the MLE remains same, because when you do the derivative, the partial derivatives, this yi will getting cancelled when you do the partial derivative with respect to mu x and sigma x. And when you do the partial derivative with respect to mu y and sigma y, that will get cancelled. This is the mathematical aspect. The logical aspect is this. Did you understand, all of you, this one? This is very important. All of you? Yeah? Understood, guys? What about others? Very good. So you have got the MLE, right? So we have got the MLE of mu x and mu y. So therefore MLE of this will be x bar minus y bar. Simple, right? So got the MLE. X bar minus y bar. Okay. Okay, tell me, what is the sufficient statistics of this? How can you find the sufficient statistics now? So tell me, if you know the sufficient statistics of theta is, let's say, t, then what is the sufficient statistics of Tn? Is it t to the power n? That's my question. The question is that if the sufficient statistics of theta is t, then what is the sufficient statistics of f theta? Tell me. Do you know this?
Yeah, it's f of t.
F of t, are you sure? How can you prove it? And what is the sufficient statistics of this sufficiency? What is the sufficient statistics of completeness? Is it also true? This is complete and sufficient, let's say. Is it also true here? Do you see the idea? It's the invariance property of also completeness and sufficient statistics. Is it true or not? That's my question to you. If it's a one-to-one transformation, otherwise it's not true. Like if t is sufficient for theta, then theta square ke liye t square is sufficient. It is not true. So one-to-one it is understandable, but what about others? Yeah. Tell me, guys, what do you think? How can you prove it, rather? So I'm asking you this because invariance property is very important. You can see from here. Also, if it's consistent, is it also true here? We have seen the invariance property for MLE and for MLE. Is it true for sufficiency, completeness, and consistency? Is it true? This is the consistency part. So is it true or not? What do you think? You need to ask these questions. Is it true or not? Because if it's true, then with the same property, we need to just find the mu x and mu y ka sufficient, completeness, consistent, and just the estimators of, like, just the estimators like this. Otherwise, it's fine, right? And just like that. So is it true or not? What do you think? What do you think? Just tell me, guys. Can you prove it? If it's one to one, then it's fine. If it's not one to one, what are the properties of f? So let's discover these properties. Okay, this is very important. You see the problem over here. So once we know all this stuff, we can even know all these things, like, Of course, it is not true for UMVUE because UMVUE के लिए extra condition है कि it will be unbiased. So all functions will not be unbiased, right? So it will not be true for UMVUE, of course. Right? It's very simple. It will not be true for UMVUE because if you take, of course, UMVUE is almost unique in all the sense. If there exists two UMVUEs, okay, let's say in some cases there exist two UMVUEs, U1 and U2, two UMVUEs, then U1 plus U2 by 2 is also unbiased, okay, but uska variance will be what? Uska variance will be what? Variance of U1 plus U2 by 2, uska variance is less than U1. What do you think? Iska variance? You don't know, okay, because you have the covariance part also, and they must not be perpendicular. So you don't know. You have calculate the variance of this and check, okay, whether it's or not. So you may not, if we don't know the UMVU part, but you can at least know about the consistency, sufficiency, and the MLE. MLE you already know the invariance property of this. Okay, so what do you think? Any theorem you know, any results you know? Because it will help you understand and do problems better like this, right? These are results that are really important.
I think if T is sufficient for theta, then Ft is sufficient for theta, not F theta.
That is true. That is true. That is true.
For F theta, T is also sufficient because by factorization theorem, joint PMF equals to something G T theta into H curve.
Okay.
And if the parameter is F theta, then G T F theta into H curve. And F theta is also a function of theta.
You're right. You're right. Just give me a moment. So for MLE, we don't need any condition. Yeah. So what Romit is saying is the following, is that he is telling the following stuff. That, okay, I'm writing down the result. He's telling, okay, there is a result for consistency, okay. The consistency tells you is that if T is a consistent estimator of theta, okay, this is actually in probability convergence. See, if theta n converges in probability to theta, then f of theta n theta hat converges in probability to f of theta. Okay, so this is true. This is true. And this is like in probability convergence. So this is true. So therefore, invariance property for continuous invariance for theta hat n converges in probability to theta, then f of theta hat n converges in probability to f of theta for f continuous. This is called continuous mapping theorem. I think I'm not doing any mistake for in probability convergence. For MLE is also true. For MLE, in fact, it's like continuous function. Maybe it's not a requirement. So if theta hat n is an MLE, then of theta, then f of theta hat n, theta hat MLE is MLE of f of theta. Okay. What about sufficiency? Let's check that. So what Romit is saying is the following. So let's take X curl. He is saying that given t, what we can write, or we can write fx as, can you tell me what we can write as fx by Neyman factorization theorem? We can write fx as
G of d theta into h x curl.
perfect, right? This is Neyman factorization theorem. So we say if we can write like this, then t is sufficient for theta. So we need to know what is sufficient for f of theta. Okay, we need to know this. So he is telling that if t is sufficient, if f of t is sufficient for theta, then t is sufficient for f of theta. This is something known. How I can show that? If f of t is sufficient for theta, let's call it g of t. Let's call it g of t. Okay, let's call it g. Let's call it m of t because there are a lot of variables over here. Let's call it p of t or s of t. So let's call it s of t. So we can write that if f of s of t is sufficient for theta, then how is st sufficient for s of theta, Romit?
No, I
Oh, sorry. If s of t is sufficient for s of theta, sorry. Okay, what did you tell? Can you come again, Romit? I think I misunderstood the problem.
I was saying the parameter, assume the parameter is something function of theta, say g theta.
So
Psi theta. Parameter is psi theta, and t is sufficient for them.
okay, telling that t is sufficient for s theta, let's say.
Yeah.
Then
s theta is a function of theta, so we can write g t of s theta as another function g1 t of theta.
okay. So it implies t is a function of theta, right? T is sufficient for theta. So can we tell the other way around? Like, we want s of theta ka sufficient statistic. You understand? We want s of theta ka sufficient statistic.
For inversible function, it is working.
Yeah. So we can only tell this if f is invertible. If f is 1 to 1, we can say this, not otherwise. If f is 1 to 1, f of theta hat sufficiency for theta if f is 1 to 1. Okay, so therefore if if so then what we can say, like, can we not therefore find out the sufficient statistics for mu to the power n? What is the sufficient statistics for mu to the power n for any let's say normal? What is sufficient for statistics for mu square? What is sufficient statistics for, what do you think? What is sufficient statistics? Let's therefore solve this problem. Find a sufficient statistics. Do you understand? This is how new problems are made, guys. You ask a question, if it's not solved, you solve. So therefore my question is that x1, x2, xn follows normal mu comma sigma square. What is the sufficient statistic for mu cube? What is sufficient statistic for mu cube? Tell me. How will you find this out? Let's this problem came. Like 1, 2, 3, 4, 5 follows normal mu comma sigma square. Like, or do the following are the sufficient statistics of mu cube? How will you find the sufficient statistics of mu cube? Tell me. It's a very important question. How do you find the sufficient statistics of mu cube? Okay, so what about mu to the power 4? Or let's say mu square minus mu. Let's find a sufficient of mu square minus mu. How will you find this? So if we can solve this problem, we can show that now we already solved the problem, okay, over here. Okay, so that what is the MLE of this? What is the consistent estimator of this? But we have not solved the mu x minus mu y. So this is the problem I will solve last. Like like today there is no time to do it. So what is the sufficient? Like, let's end this problem. What is sufficient size of mu square minus mu? Yeah, what do you think, guys? What is sufficient size of mu square minus mu?
It's a one-to-one function, so like we just need
to. It's a one-to-one function. It's a one-to-one function.
How?
Huh?
If we can find for mu.
F of x square minus x square is a one-to-one function.
No, not one-to-one, but like we can find individually the sufficient statistics and then.
So that's what we have understood. It's not happening. It's not provable. So how do you find the sufficient statistics of mu square minus mu?
So intuitively, sufficient statistic is a statistic which contains the entire information about the parameter.
Right.
Then it should contain the entire information about the parametric function also.
So how do we prove it here? So therefore you're telling that if t is sufficient, t is also sufficient for f of theta. How can you prove it?
For sufficient statistic, feature information based on sample is feature information based on that statistic.
My question is that how do you prove that sufficient statistic, if t, you are right that if t is sufficient for theta, then intuitively t contains every information about theta, any function of theta, right? if you know the function. The question is therefore, how do you mathematically show it? That's the question. Here in this result, how do you mathematically show it? Tell me. How do you mathematically show that? Yeah, tell me that. So this question came in IIT this year. Find the sufficient statistics of mu square minus mu. Like 3 options are given. So how will you show it? Like let's find the mathematics part only. How will you show it? Forget about the rest of the part. Tell me. What do you think? Like this question came in IIT this year, you have 5 minutes to solve it. So solve it right now. If x1, x2 follows normal mu comma 1, let's say forget sigma square. Find the sufficient statistics of mu square minus mu. How will you mathematically show it? Tell me, guys. Tell me. You know this. I know you can do this. How will you show this? So this is a question for you. Find the sufficient statistics for mu square minus mu right away. Yeah. Romit, Nikhil, Polomi, Sriteja, Shoikot. Or maybe is it a good question to ask? It's a good question to ask, of course. But how to find a sufficient statistics of mu square minus mu? So what we need to show? So this is a parameter of normal. Let's call it theta.
If we go with definition, the conditional distribution of the sample.
Go ahead. Yeah, go ahead. You're on the right track.
Conditional distribution of the sample given the sufficient statistics free of theta. Then it is free of something function of theta.
Very good. That's it. Very good. That's the idea. That's exactly the idea what Romit told before. That if you know everything about mu, therefore you know everything about g of mu, right? So if it's independent, if it's free of theta, if it's free of mu, it's free of g of mu. So therefore, if t is sufficient for theta, t is sufficient also for f of theta. So this is not required. All of you understood this, guys? Does it make sense? if x bar comma y bar is sufficient for mu x comma mu y. Now here comes the idea, is mu x bar minus y bar sufficient for mu x minus mu y? This is something you must ask yourself. For that, you have to condition of x bar minus y bar and see whether it's independent of mu x minus mu or mu x minus mu y or not. You do that, right? The question is therefore, now the question is to you is this. The final question, very good Romit. The final question is this, that if theta hat 1 is sufficient for theta and rho hat 1, rho hat and theta hat is sufficient for rho, okay? So is rho hat, okay, let's do it for normal only. So let's do it like, you know, x1 x2 xn follows normal mu x comma 1 and y1 y2 ym follows normal mu y comma 1. So we know that sufficient is this, is mu x sufficient and x bar is y bar is sufficient for mu y. My question is that how will you show that you know therefore mu x comma yx is sufficient for mu x comma this is also sufficient, therefore sufficient for mu x minus y. But we want to know that if this is sufficient, then is this is sufficient for this. This is the problem now. Is it sufficient or not? That means, do you want like x bar minus y is sufficient for mu x minus mu y? You think about this problem. Also try to find the other problems, you know. The UMVV, the completeness, all this, find out this problem, likelihood ratio test. So find out this problem. So these are the problems you should ponder upon instead of doing the past papers all the time. These are the things that, you know, just to stimulate your mind. Do you understand this, guys? So what do you think? This is a sufficient statistics or not? So think about this problem. Till then, I will say goodbye. And I hope you enjoyed the class, and I will see you in the next class. If you want to continue this problem next class, we can, or else we can do something else. Bye bye.